I guess, is that good?
Yes, it's good now, yes.
Okay, let me move this thing really fast. Hold on 1 second. I guess that'll be, let's put that there and let's get rid of that. Okay. Okay, so we're good to go?
We're good to go. It's a great pleasure to welcome Morgan Henry Lynch, who is going to tell us about Unruh, the Unruh effect in particle physics. And he's joining us from Seoul in South Korea. Thanks, Morgan. I hand it over to you.
Yep, thank you very much for the opportunity to present here. As you know, I'm a big fan of these DIAS seminar series, and so it's a very big honor for me to present my research for you guys. As it says, the title, At Gravitas, an exploration of the Unruh effect in particle physics. And so what I'm going to talk about is a recent analysis of an experiment that I analyzed, which was carried out by the NA63 collaboration at CERN. And so I figured what I would do is give a little bit of background in quantum field theory and curved spacetime, and then just kind of take you along the pathway that I took to essentially understand this experiment. And so all right, so to begin, okay, we have our timeline and milestones. So we'll go over a little bit of the background. We'll talk about the beginning of quantum field theory and curved spacetime with Schrodinger, and then eventually Parker, Hawking, and Unruh effects. And all these lead to basically spacetime thermality and attempts to measure these things in analog gravity. Then we'll bring up these new results, specifically this radiation reaction channeling radiation experiment, which was designed to measure radiation reaction, the analysis we did with that. And then we'll talk a little bit about potential future analyses and things that I'm working on currently here at Seoul National University. And so the general idea of the way I was approaching this research was to look at particle physics using techniques from quantum field theory and curved spacetime. And rather than looking at, say, momentum transfer from particle collisions, looking at strongly or extremely accelerated currents and radiation emitted from that, which incorporates things like the Unruh effect and things like that. So we'll be looking at QED and curved spacetime and what that has to say about channeling radiation. So I guess let's just go back to the beginning for a historical introduction to everything. Quantum field theory and curved spacetime actually began with Schrodinger. After he had developed his wave equation, he wasn't resting on his laurels and immediately incorporated his wave equation into the curved spacetime settings that were being developed by Albert Einstein. And what he had found was that if you have a wave equation and an expanding universe, you essentially get a runaway creation of particles, and it gives you like an Olbers type of paradox where you can get a universe which is completely saturated with photons.
Excuse me, sorry, may I interrupt?
Yes,
there was
yes,
another, sorry, there was a physicist before that, Schrodinger, in Russia, who wrote a paper on scattering of gravitons. Actually, he was jailed and then executed by Stalin.
Really?
Yeah, I am trying to remember the name. It's quite well known, actually. So he was.
I'll try to look that up, actually. I would like to know who that is. Actually, it's an interesting story.
But he wrote, it was the first paper on graviton scattering, which he calculated.
So it's graviton scattering, and he saw the same type of effect?
He found the cross section. So it was the first attempt to go into quantum gravity.
Ah, interesting. I actually have something I can add on to that too. I'll explain that one in a second. That's interesting. Well, thanks for mentioning this work, actually. I'll have to look at this. It's an interesting story.
Yeah.
Okay, so building upon this work, Schrodinger also found a runaway solution of creating particles by an expansion universe. I was looking up the date about this, so I'm not too sure exactly when, but I believe Schrodinger first showed up at the DIAS around 1939. So this paper might have been done while he was there or shortly before he got there. Something very right in this time frame, though.
Yeah, he arrived in DIAS in 39. That's correct. Yes.
So cool. So okay, this is interesting. So I guess this is founded at the DIAS as well, which I thought was kind of cool. And so what you have with this, though, is if you just go back to standard undergraduate quantum mechanics and just look at a particle in a box and you analyze the incredibly expanding box, when you expand it, you get non-zero probability to populate these excited modes. And in a second quantized setting, these probabilities become real particles, and so you end up with this runaway particle creation. And so this was a persistent problem that was there in the field until Leonard Parker, about 30 years later, incorporated the Bogoliubov transformation into these theories, which resolved this paradox. So let's talk a little bit about this Bugel-Bott transformation. So in general, if you have a wave equation in a curved space-time, typically what happens is you have your standard wave equation and then some exotic potential which captures all of the curved space-time effects into it in terms of an exotic potential, right? And it could be time dependent, spatially dependent. And if I just look at two different space-times or two different vacuum or two different quantization procedures, right? You can define your states, okay? If I quantize in one space-time, I'll have positive and negative frequency mode functions, say F1 and F2, with their associated and creation and annihilation operators. And if I can define a different vacua, or say a different, same space-time, but at a different time for an expanding universe, I also have a complete set of positive and negative frequency solutions with their associated creation and annihilation operators. And because these things form a complete and orthonormal set, I can rewrite, say, the second quantized field from vacuum 1 as a linear combination of the modes from vacuum 2 or space-time 2. However, since they are second quantized fields, you have to map the creation and annihilation operators to each other as well. And this is what's known as the Bugel-Bott transformation, essentially like the completeness relation between the operators, right? And the interesting thing to note is that for each, say, destruction operator or creation operator, you have a mixture of the creation and annihilation operators of the other space-time. And if you note, it's these alphas and betas are the Bugel-Bott coefficients, right? And if you note that the beta Bugel-Bott coefficient is the one that's responsible for always mixing the creation and annihilation operators, or particles and antiparticles. And one of the things that we can do then is ask the question, if I change from one space-time to the other, how many particles, say, from space-time 2 are present in the vacuum of space-time 1? And that number operator ends up giving you this beta squared of these Bugel-Bott coefficients for both cases. So number of particles from space-time 1 in the vacuum of space-time 2. And so this technique of mapping the creation and annihilation operators kind of tames a lot of these computations that people were doing and lies at the very foundation of quantum field theory and curved space-time. And so now let's look at how Parker incorporated this into this runaway paradox of particle creation, and was able to temper these particle creation. And one of the things that he had found, or how this works, was he found that for conformally invariant wave equations, so that's massive scalar particles or massless spin 1 particles in expanding spacetimes are conformally invariant. And so you get no particle production. As Ball was saying, I believe for massless spin 2, these are not conformally invariant. So that runaway particle production, that thing persists as well. So the fact that that's there is I guess, consistent with what Parker has found as well. Now, Parker had found the number operator for the distribution of particles that were created, but he had no idea at the time that these things were going to be thermal. It wasn't until, I think it was probably Bekenstein, who introduced the notion of entropy into black holes in these curved space-time settings, that people were starting to think about thermality. Anyway, Hawking found the thermal distribution for black holes, and then Parker went back and looked at his results and indeed found a thermal particle production by an expanding universe where the temperature is determined by the essentially the difference between the initial and final scale factors divided by the initialization time, say a Planck time. And so he found a thermal distribution of particles. The big one, Hawking, looked at the Bugel-Bott transformation between an initial space-time filled with dust collapsing into a black hole, and found that the distribution of particles was a thermal distribution where the temperature is the surface gravity of the black hole. And what's interesting about this one is when you put in all the physical constants, you have Planck's constant, so it's quantum. You have capital G, so it's gravitational, so you have a bona fide quantum gravitational quantity here. But also you get KB, you get thermodynamics as well. So this has this really interesting phenomenon of mixing all of the fields of physics, not like quantum fields, but the subjects of physics. You have statistical mechanics or thermodynamics, quantum, and GR all in one setting. And this caused a little bit of a flurry of work. In particular, what had happened was Bill Unruh then was looking at the near horizon limit of a Schwarzschild black hole and was putting particles in boxes next to it to see if he could absorb this. Now, that near horizon limit of a Schwarzschild black hole is vacuum Minkowski spacetime, but in an accelerated reference frame, which is Rindler spacetime. And he indeed found that the transition rate of a particle in a box absorbing this quanta would have a thermal response function, but which implied that there was a thermal creation of particles produced by moving into an accelerated reference frame. And this completes the work of Stephen Fulling and Paul Davies, who had been culminating, their work was culminating into this understanding of this thermodynamic nature of acceleration. And you had mentioned that you were up there with Rafi Sorkin. So I was a visiting graduate fellow up at Perimeter with Nayesha Shorty, and was in the same group as Rafi. Here you have Don Page, Steve Carlip, and of course Bill Unruh. Yaseman, I believe, was just up there a couple months ago for there was a theoretical physics conference there, and she was presenting there, I think. And this is at her graduation. And so what we have now is these particle production mechanisms are developing this thermodynamic understanding of space-time, and this culminates in basically with this, well, let me show what it culminates into. So the first thing was that Bekenstein had predicted that there was going to be an entropy associated with the area of black holes. He didn't know what the coefficient was, just that it was going to be proportional. And so what Hawking did, now that he had his temperature of the black hole, he was able to basically just plug it into the second law of thermodynamics theory. He has his temperature, he plugs it in, and he just takes a piece of mass and throws it into a black hole. And then you can integrate this up to find that the coefficient is 1/4. So that the area entropy ratio is 1/4. And this is now known as the Bekenstein-Hawking area entropy law. And then a little bit later, Ted Jacobson, building on this law here, was able to look at essentially a kind of a causal diamond of a Rindler observer, okay? And so if you have a Rindler observer that's accelerating, there's going to be a Rindler horizon at a distance 1/a, say, beneath it, right? And if you are emitting radiation or any sort of energy momentum into this horizon, you can compute the total amount of energy momentum which is sensed by these null rays. So you can define an initial area which is spanned by these null rays, right? And these null rays get contracted with the energy momentum tensor and then integrated over the volume. And this tells you the total energy that goes through the horizon. At the same time, this energy momentum will give you a source of curvature, Raychow-Dury curvature from this Ritchie tensor here. And the geodesic deviation of these null rays by that curvature stretches the horizon area, okay? And if you use the hypothesis that this area will be proportional to the entropy, okay, and then formulate the second law here about these quantities, you can unwind these integrations, and what you get out is the Einstein equation. And so the end result is that there is a thermodynamic kind of equation of state associated with these quantum fluctuations, which implies that maybe gravity is kind of an emergent quantity from these quantum fluctuations. And so this is kind of the culmination of this quantum filter and curved space-time idea. And so what we can do now is kind of switch gears and talk about techniques and attempts to measure these things. So this brings us into the field of analog gravity. Going back again to Bill Unruh, when he was at Vancouver teaching a class, I believe, in fluid dynamics, he sees that there is an analog of the wave equations in a fluid regime with particle or wave equations in curved spacetimes. And he was able to map these things together so that you can analyze simulations of all of these phenomenon using fluids, right? And this has led to an explosion of work in the community. We have super radiant scattering from Silke Weinferner out at Nottingham, the upscattering, the up frequency of the of incoming waves by the rotation of a black hole. We have actual stimulated Hawking radiation in fluid flow over a wing here, where you have a sonic horizon and you get a thermal distribution of particles created from that. We have, this was across the way from me when I was back at Technion, Jeff Steinhauer making spontaneous Hawking radiation in his analog DECs. There you have a sonic horizon there as well. Also, Steinhauer, working with collaborators in France, were able to look at an analog expanding spacetime and see the Parker effect. What they did is they had a gas of rubidium atoms and they shot a laser through it. And from the nonlinear Kerr effect, you had a self-focusing of the laser spot. And then when it exited, you had an expansion of the laser spot size, and you see these momentum interference fringes. And it has a curious structure, which is very similar to those baryon acoustic oscillations in the CFB. And so you have a lot of these phenomena which are now being explored experimentally in an analog sense and all together. And what we would like to do is see if we can find a fundamental system to analyze these things.
Sorry.
So now,
yeah, and if I may, yeah, it was moving a bit too quickly for me. So here, I mean, obviously the baryon acoustic oscillations looking similar to this is really intriguing. But so is this similar to gravitationally producing particles, or I mean, yeah. Why is there this similarity? Are you getting to it? Is this accidental?
So this is one thing that I've actually been confused about myself. From what I always understood is that you have some inflaton. The inflaton causes the universe to expand. You have the Big Bang. This inflaton decays and creates all the particles that are populating the universe. And so you end up with this, we'll just call it a fluid, right? And then there's just sound waves in this fluid as it's expanding, and that's what these things are, right? That's the kind of standard thing I think they teach in like cosmology classes. I think Larry Ford had a paper that came out that all of this matter that you see is actually coming from the Parker effect. It's actually created from the expansion of the universe, that the particles are created by this effect, which is what I always kind of interpreted it as being. And I think this honestly kind of shows it in an analog setting. And so this is where I get confused with, maybe I'm interpreting what the Parker effect is incorrectly, or maybe I'm not paying attention enough in class. But I've noticed the same thing I'm kind of struggling with how to interpret the two things together. Yeah. But it's very, I think it's a very intriguing result. Very intriguing indeed.
Yeah, I mean, with the inflaton and the fact that it kind of reheats the universe by basically decaying to standard model particles is one idea. But I think what you're describing is a lot kind of closer to this new early dark energy models, which, I mean, it is absolutely fascinating.
Yeah, no, this one was really cool. And what I really liked about this, what was actually very interesting about this one is because they can, so you have this gas of rubidium atoms that are in this cavity right here. You can perturb it, you can hit it with a magnetic field, you can tailor make an initial state. Mm-hmm. And that initial state shows up as in the low frequency regime here. And this is where you get information about like essentially the initial state of the Big Bang. And so if they can do some like higher precision models, measurements of like the CMB, they can basically do analog experiments to see what that initial state of the universe was. It's really, really fascinating experiment.
That is absolutely amazing because, as you know, we only have the one experiment, right? Universe, it just happened. We look at CMB. This is absolutely fascinating.
Yeah, this one was, I was definitely impressed by it. Yeah, because I always thought that these things would come from Parker effect, but I don't know. I was always afraid to say it because I thought I get in trouble or something like this. But like, yeah.
Well, Morgan, maybe I can make a comment as the one analog gravity expert in this round here. I mean, the inflaton, we modeled the inflaton back in 2004 in the two-component BC. So we showed that exactly the same equation of motion can be obtained. I mean, you can have a fluctuation field in a BC, which exactly has the same equation of motion like the inflaton field. You can model the zeta universe. You can model exactly the same equation of motion. You can model exactly the same freezing leading to galaxy formation. So density and homogeneity in the BC.
Okay, so these things can be just different names of essentially kind of the same phenomenon.
It's the same thing. I mean, the equation of motion is just the same.
Yeah.
Okay, so
you can quantize the field just like you can quantize a field in an expanding curved spacetime.
Okay.
That's amazing.
There's no formal difference. The formal difference which exists to gravity is that there's no gravity proper at all. There's no Einstein equations.
Yeah.
There's no self-consistent solution of the matter content together with the curvature of the spacetime, because there's no Einstein equations. That's still a missing link in the analog gravity program.
I see.
There's also ideas to resolve this issue, but so far the experimentalist prepares the curved spacetime, and it's a fixed curved spacetime arena. But it's exactly like what Hawking did. He made a calculation which neglects completely back reaction. That's what he explicitly mentioned in his papers, in his 74, 75 papers. The difficult issue of the back reaction is excluded.
I see.
And one more question, Morgan. The plots that you're showing now are from this paper from 1980s?
Which plot?
The one that looked like the baryon-acoustic oscillation.
Yeah, so this is a new one from so Steinhauer just put this one. This one might not even be published yet. I'm pretty sure it's published by now, but yeah, this was his latest paper. I think it's it might be another Nature.
This investigation is cosmological particle production in a polariton system.
Say that again.
So, in a polariton system.
Mm-hmm.
It was published, I think, in Nature Physics.
Yeah, so this was his latest one. Yeah, so so Steinhauer actually, yeah, he has Hawking and Parker effects now, which I thought was pretty interesting. But yeah.
But presumably it's available on the archive.
Yeah, absolutely. Yeah. I believe he presented this somewhere recently. I think it was in a Zoom conference back during all the Corona lockdowns, but I can't remember what it was. But yeah, no, there might be a video of it online as well somewhere.
Well, he did this work in Paris, so.
Yeah, he was on sabbatical.
Not done at the Technion.
Yeah.
Can you repeat what the system was? Just what the you're talking about the bottom graph here, presumably.
Yeah. So I forget what the fluid was. It was some I don't know if it was a BEC or some ultra cold gas.
It was a BEC of polaritons.
A BEC of polaritons. Okay.
Okay.
Yeah, and then the laser goes in, and so then you get the nonlinear curve that gets self-focusing of the laser, and then when it comes out, then the laser expands back out.
Okay, and I just wanted to check that quantum effects were essential in this.
I believe so. Yeah,
it's not just hydrodynamics. The quantum effects.
It's either, I'm not sure exactly. It's either quantum effects or nonlinear electrodynamics is going to be I'm not too sure which one specifically.
Okay.
But I know,
all right.
Yeah, but yeah, one of the two. Yeah.
Okay, I'll have a look at that.
I would still think cosmological particle production is a genuine quantum effect.
Yes, absolutely. That's why I'm asking.
Yeah. Okay.
In this case,
you can call it dynamical Casimir effect or cosmological particle production. It amounts to the same.
But the question was whether it's quantum. Whether it's the quantum aspects of this analog system that are essential, or it's the fluid dynamics.
Well, I mean, the background is, if you want the space-time background, is furnished, of course, by the fluid dynamics.
Yes.
There's no Einstein equations, as I said.
Yes, absolutely.
Yeah.
Okay.
Okay. Yeah. So at least there's lots of interesting systems to study with these things now, and there's really a lot of interesting questions, and in particular, this one I think, yeah, is definitely bringing some very intriguing insights into things we can simulate with these analog gravitational systems.
Question.
Question?
Yeah.
No, go ahead.
Yeah. Do you have an analog of Wittgenstein-Hawking entropy also here?
In these, okay, so as far as I know, none of them is looking at. I'll have a couple things to say about that later on with the Unruh stuff that I'm doing. The closest thing that I've seen to anything regarding entropy or anything like that is more of entanglements or correlations that you see. And I know what Jeff has is, because he has I call it the bird's eye view. He's able to look at the pairs that are created both in and outside of the horizon, and he's able to see correlations with that. He calls it the mustache, is what he's calling it. But you can see the definite correlations between the Hawking pairs, and whether or not you can assign entropy, things like that. But that's so far the closest that they've got to actual looking at any sort of correlation, any sort of things beyond the actual just production of modes.
Okay.
And but for area entropy stuff, I did take a stab at looking at area entropy laws for the Unruh things that for the Unruh analysis of the channeling oscillations.
I should insert another comment here.
Say again?
There is no area entropy law in the analog black holes because there is no Einstein equations. The area entropy law relies on the Einstein equations. Without Einstein equations, there's no area entropy law.
Oh, well, if that's
because the area must be increasing, and that really follows from,
yeah, and also I think, because I mean, these are, I don't know if these are effectively one-dimensional horizons or something like this. Yeah, I don't know exactly how these things would work. Yeah, I don't know. So yeah, if there's no gravity, then yeah, I don't know. Yeah.
Okay. Thank you.
Okay. Well, fun. So this so we got some good discussions going. Okay, so yeah, so as you can tell, I mean, this is a flourishing community now, and yeah, so the main goal was looking at, it's difficult to find, say, Hawking radiation from actual astrophysical black holes. I would mention that Nayesh Shorty might have I guess an analysis demonstrating that, but that's still ongoing. But short of actually going out to a black hole, it doesn't seem like you'd be able to find Hawking radiation in the laboratory setting. Parker effect might be able to be found in the CMB. That's another avenue that people were looking at. And so the notion of looking at acceleration or the Unruh effect using particle physics, which is essentially the strongest types of accelerations we can produce in the lab, that was kind of what prompted toward looking at the Unruh effect as a fundamental system. And so let's, I guess, start switching gears now to looking at QED, Unruh effect, and radiation emission in QED, looking at using these strongly accelerated currents. Okay, so starting up with Unruh DeWitt detectors. Unruh DeWitt detectors are really good at analyzing radiation emission from accelerated sources. You can even use them to model elementary particles. Just take a two-level system, accelerate it, have something come out, and that's a model of looking at radiation emission. And so if I have a uniformly accelerated Unruh DeWitt detector, I can emitting a particle with it undergoing a transition. Okay, I can model that interaction with this interaction action here. We have the particle phi here, which is emitted, and the monopole moment operator, which is like a creation and annihilation operator, which induces transition in your detector. And if I just look at the emission of a particle from the vacuum, coupled with the simultaneous transition in your Unruh DeWitt detector, and I want to analyze the transition rate or the emission rate, I get what's known as the response function, which is the Fourier transform of the two-point function and of the particle emitted. And if I evaluate this thing along a uniformly accelerated trajectory, I get a thermal response function. And here we see the thermal distribution with the temperature, with the temperature being the Fulling-Davies-Unruh temperature. And so what we want to do then is take this kind of generic emission of radiation and bump it up to the QED interaction so that we can analyze experiments with it. Okay, so let's look at Cherenkov radiation. This serves as a really simple example because everything is basically delta functions. The math is a lot easier, right? So if we look at Cherenkov, right, if I have an index medium, okay, and if I'm traveling faster than the speed of light in that medium, you emit superluminal booms in analog to sonic booms from breaking the speed of sound. And the emission spectrum is known as the Frank-Tan formula. It's a very simple formula. And all of the radiation that's emitted gets dumped into a cone, a Cherenkov cone, which is defined as 1 over n beta. And so you see that if the index of refraction is 1, you can't have any emission. So you need to have the index present. And everything gets dumped into the cone here, as you see. And so what we want to do is reproduce these results using an Unruh DeWitt detector. So to begin, we start with our QED current interaction. A mu is our photon, J mu is our semi-classical vector current coupled to an Unruh DeWitt detector. And when we compute the response function, we have our QED response function, which is that same Fourier transform of the two-point function, except we have the 4 velocities of our detector contracted with the polarization indices of our photon, okay? And so this is essentially the square of the V dot A interaction is what you see here. And if I evaluate that two-point function along a constant velocity trajectory, okay, I do indeed, or you do indeed reproduce that Frank-Tan formula, okay, and your Cherenkov cone. However, the presence of that energy gap manifests itself by deforming that Cherenkov cone, okay? And so what you get then is if I have an excitation in my detector, you take the standard Cherenkov cone and it bends it in, it makes the cone smaller. And if I have a decay, it bends the cone back out, okay? And what's also interesting with this that I noticed is that if you have what's known as the anomalous Doppler effect, right? So if I have a co-moving oscillation, I can incorporate that in the Unruh DeWitt detector by just taking that frequency of oscillation and just putting it in there. Okay, so that right there gives us one clue that if I have a co-moving oscillation in an Unruh DeWitt detector setting, I just put that frequency in there and it's a term in an energy gap thing. Okay. Second thing that I saw, the recoil correction, right? We want to look at radiation reaction. The recoil correction in Cherenkov is known. It's inertial. It's like an undergraduate problem, very simple problem. And one of the things that I noticed is that if you set this energy gap to this specific function, you can incorporate the recoil correction to Cherenkov radiation. Now, rather than just kind of ad hoc putting in some function, we wanted to ground it in the literature with something, some physics behind it. And for that brings us to incorporate recoil. We use mass renormalization. This is specific to Cherenkov, the mass renormalization, but let's talk about what happens, okay? So if you define your energy gap as the difference between the final and initial energy of your electron, what you have in an indexed medium, the mass renormalization, is your electron. Before it emits the photon, it builds up around the electron and forms like a little vacuum polariton atom thing, where you have the nucleus as the electron and the photon forms a shell around it, and it renormalizes the rest mass with that photon frequency, okay? This thing then decays like an atom, And it has a kick, a recoil, which gets enhanced by the index of refraction, the momentum enhancer from the index of refraction, okay? The difference between the initial energy, mass normalized final energy with the recoil kick, and this gives us a recoil kinetic energy with that momentum enhancement produced by that mass normalization. This is the recoil correction to Cherenkov radiation, right? Was originally worked out by Sokolov, the mass normalization by Sidovich, okay? And so if we incorporate this term in the energy gap, we get the recoil correction to Cherenkov radiation, right? Now in vacuum, you don't have any mass normalization, so you just have the omega squared over 2m term, okay? And so now you can just kind of by eye see that this is a process independent recoil. Just whatever happens, the recoil gives you a kick. And so if I want to incorporate this type of recoil in Larmor radiation, now we have radiation reaction, the standard problem radiation reaction.
Sorry, but n is equal to 1 in vacuum, so this term disappears.
Yeah, no, if n is equal to 1 in vacuum, that term disappears. But you don't have mass renormalization, so you don't have the 1 in vacuum. It's the mass renormalization which gives you that.
Okay.
In the medium, you get mass renormalization. Without the medium, you don't get. If you do like you see this in heavy ions, when you have like the quark gluon plasmas, you get the rho mass broadening, you get the smearing of the mass due to the medium. But yeah, so in vacuum, you don't have the mass renormalization. So this term is gone, and then you just set n equal to 1, so just omega squared over 2m. But so the idea then is to take a recoil correction like this, incorporate it into Larmor, and then we have radiation reaction.
Sorry, may I ask a question here?
Yeah.
So you're assuming that this energy difference, this delta E, is always positive, is that right?
It can be negative too.
So what would mean your n is between 0 and 1?
No. Okay, so no. Think of it like it's a little bit, okay, so let's say I'm in a stationary frame, the photon's emitted, right? So the kick, I see an increase in kinetic energy, okay? So it's positive. Then let's say it emits another photon. It kicks it a different way. It slows it down. Now it's negative.
I see.
Yeah, so you're looking at jiggling, kicking, moving, and spin flips and things like all of these little jigglings and things like this, which increases the energy from some initial rest frame. And then so you get the kicking around.
And so this is a really stupid question. So the viscosity of the medium doesn't come into play at any point?
The what? The viscosity?
Yeah.
In the Cherenkov sense?
Yeah.
I'm pretty sure in a realistic scenario, sure, but this is just a pure, theory calculation. Viscosity of the medium. Yeah. I mean, it would probably give you some extra, but probably Bremsstrahlung.
Yeah.
Something like this. Yeah, it would probably, some other stuff that's happening. Yeah, sure, yeah, absolutely. But this is just pure, clean Cherenkov radiation.
Thank you.
Okay, and so then now let's go ahead and switch gears a little bit to just the standard problem of radiation reaction.
Sorry to keep you back, but I didn't actually understand your mass renormalization. I thought it was the omega was supposed to be interpreted as a mass renormalization.
This is, so this term, so the initial state of the particle is not just the electron. It's the electron with the photon that's about to be emitted, that's sticking to it somehow. And so this new hybrid object is the initial state.
Okay.
It's dressed.
That's fine. But I don't really understand your formula, how I can use your formula when n is equal to 1 then.
In vacuum, there's no mass renormalization. In vacuum.
And vacuum, there's no mass renormalization, and I should include the omega in the other term.
Yes, and the omega in the other term.
Okay.
Yeah, so that means this term is gone in vacuum. And
okay, no, I see your algebra then. Okay.
Yeah.
Okay.
Is this okay?
Yeah, that's okay. Yeah.
Now, in principle, this at the same time, this is a hypothesis. It is a hypothesis. So there could be some other things happening, but yeah. I'm not insisting that this is the real case. This is a hypothesis that went into the analysis. Okay.
One question.
Yeah.
Go ahead.
So how do you get this delta E to be negative? Like from the equation? except for n coming in between 0 and 1?
No, it comes from, well, at least the way I understand it in terms of, as we'll see with the Unruh effect stuff, but it's, you have an initial reference frame, and the particle gets kicked around. So if you want to think about this in terms of a kinetic energy, that kinetic energy can increase and decrease relative to your initial reference frame. So the first one, it kicks, it's a positive increase. Then the next one, let's say it increases it again. It's another increase in the kinetic energy.
Yes.
But then let's say the photon emitted in an opposite direction, then it decreases. Something like this.
Okay, but that I don't see it from the delta E expression that you have here.
Well, there is. So maybe it's something like this, right? Well, I know that.
I think the equation needs some small little bit of regeneralization, because it's you're trying to extract too much from it, from this brief equation, Morgan.
Well, in terms of it being negative, well, if you want to put it, I know in the Unruh effect sense, it can be negative because those sort of things happen. But in Cherenkov, but that's a statement of detailed balance. That's a whole other thing with thermalized systems. With this one, I think. No, it would have to be. It would be stimulated inverse. It would be inverse Cherenkov radiation. I think what that would be. If it was negative, it would be an so in this case, what you have is the kick, which slows it down.
Okay.
And then if you have, and this is, if I have incoming laser light at the same Cherenkov cone, which is used to accelerate it. So this is using Cherenkov radiation to accelerate the particle. I think it would be, it's a separate type of scenario. I think I'm confusing the thermality that you get with the Unruh effect. For this thing to be negative, I believe that would be inverse Cherenkov radiation.
Okay.
Which is a different phenomenon. In the Unruh setting, we were talking about like, you know, transitions up or down of your detector at thermal equilibrium, the jiggling of the detector. But yeah, in the Cherenkov sense, you don't have thermality, so I don't think you sum over transitions up and down. Okay,
that's fine. I think it's clear. The physics is relatively clear.
Okay,
the formula is just a little bit too brief, and I tried to read too much into it.
Sure. And you know, this was trying to make sense of how to incorporate this recoil with the Unruh DeWitt detector. It was, you know, we knew what the kinematic recoil correction was, and then if we set the energy gap equal to this thing, it reproduces that. So we're trying to cobble all these pieces together as sanity checks to reproduce known results. The interpretation of what happens, I guess you could say, is still a work in progress, so to speak. Okay, so now let's go to just the generic problem of radiation reaction. So here what you have is the standard Lorentz force equation of motion. And then if you then just to take the Larmor formula, which is the radiation emitted, and just integrate that into the change in kinetic energy, you have the standard Lorentz-Abraham-Dirac equation, which is the recoil correction here. Now, the fact that this is a second order derivative on the velocity, or a third order derivative in the position, so it's a jerk term, this leads to runaway solutions. So if you just kind of touch the particle, it'll spontaneously self-accelerate up to the speed of light. And so another way to think about this one, though, is if I accelerate, or if I oscillate a charge or accelerate it, right, that oscillation frequency sets the energy of the photon that's emitted. The energy of the photon that's emitted is set by that, or sets the recoil, the kick, and that recoil then changes the acceleration. And so you end up having kind of a chicken and egg argument about how the acceleration, the frequency, the energy, and acceleration all talk together. And so finding equation of motions which incorporates all these things has been a pretty difficult problem. And I think it goes back to 1890 when the Larmor formula was first written down. And so this is why we want to try this new technique with this Unruh DeWitt detector, just incorporating that recoil kinetic energy and the energy gap. And so the experiment, the channeling radiation experiment, is analyzed using this, not my analysis, but the one from the paper, using this Lorentz-Abraham-Dirac equation in various approximations. There's Landau-Lifshitz equation, or using this in Monte Carlo simulations. And so this is what they use to analyze their experiment. So let's look at that experiment, okay? This is the CERN NA63 collaboration at CERN. They have 178.2 GeV positrons, and they fire these into samples of crystal, of silicon crystal, amorphous for Bremsstrahlung, and single crystal for channeling radiation. And in the channeling regime where it's single crystal, you have a regular atomic array, and that you can align the crystal lattice along the beam so that when the beam penetrates, it essentially acts like a waveguide. And so the positron will oscillate back and forth as it scatters across the sites, emitting radiation as it does so. And so if we collect the radiation, here we have the power spectrum. That's energy per unit time per unit frequency. Black dots are the data points. And the various colored curves here are the standard catalog of radiation reaction models. LAD equation, Landau-Lifshitz equation, Monte Carlo simulations of them. And one that I would like to point out in particular, though, is the red one here. This is the quantum radiation reaction model. What this one is whenever you have only the Lorentz force, no recoil corrections, no nothing. Lorentz force, and then they have a recoil correction to the quantum recoil correction to synchrotron radiation from Ritas. And what they do is they evolve their system with the Lorentz force and then take the emission spectrum from Ritas and then subtract off that photon frequency by hand. And this is what they get. And this is the one that you can see is actually kind of the closest one to fitting the data. Where it deviates is in this low energy spectrum here, okay? And what we'll see is that when we apply the Unruh effect theory, it also deviates in this low energy spectrum, but fits quite well at the high energy spectrum. And that's the one that most closely resembles what we're doing as well. Okay, so this is what we want to analyze. And so we want to take our Unruh DeWitt detector formalism and apply it to this setting. So first thing we need is that Larmor power spectrum. Starting again back with our QED current interaction, our 2-point function contracted with our velocities, and we want to evaluate it along a uniformly accelerated world line. Okay, we compute the power spectrum, just multiply the response function by an additional factor of frequency. This is the expression we get. A couple things to say about this. It's just the sum of 2 Henkel functions, these 3 Henkel functions. These last 2 are from the polarization, so this is the fundamental, the scalar component. What you see though is that the index presents itself here in the, or the energy gap presents itself here in the index, okay? And there's a Henkel identity or a Bessel identity where if you flip the sign in the index, it spits out an exponential term here, okay? But flipping the sign in the index for us goes from switching from the energy gap to excitation to de-excitation, okay? So whenever we flip that sign, it gives us this Boltzmann factor at the Unruh temperature. And so this is a statement of detailed balance by flipping the sign of the energy gap, okay? So this is a rigorously thermalized power spectrum by Henkel identity, okay? Which I always thought was pretty interesting. Okay, so this is the spectrum that we want to apply to the data set with the idea of looking at the Unruh effect. However, just because that this thing is a thermal, looking power spectrum, how do we know that we're actually looking at the Unruh effect? And in order to confirm that, what we do is we turn to the Rindler frame computation, okay? This is a prescription set forth by Matza, Spanzella, Landolfo, and Gabby Cozella, okay? What you do is if you have, and as this was a proposal that they made for measuring the Unruh effect, if you have a longitudinal acceleration with a co-moving cyclotron oscillation, okay? The particle that's oscillating will resonantly couple with Rindler particles from the Rindler bath, whose energy at the Rindler frequency, whose energy is determined by the frequency of the particle's oscillation, the amplitude of that oscillation. And those specific frequencies are the ones that you resonantly couple with from that Rindler bath. And you have to emit and absorb them, both of them, transitions up and down, emission and absorption, okay? And what they proposed was to leave the temperature of that Rindler bath arbitrary. The hypothesis is that it's the Fulling-Davies-Unruh temperature, but if you leave that temperature arbitrary, you leave it as a free parameter in your theory that you can go and measure from the data, okay? And how that's accomplished is by looking at the absorption of those Rindler particles and the emission of those Rindler particles at that specific Rindler frequency, okay, which is set by this co-moving oscillation and amplitude, okay? And if you sum over both emission and absorption, you end up with this thermal factor here, okay, as a function of the temperature and the Rindler frequency. Now, since these processes should be a covariant descriptions of one another, this Henkel function stuff we had, this process here, right? In the Minkowski frame, we had that statement of detailed balance, right? So when you sum over transitions up and down, you end up with this thermal factor, okay? Now, when you set the energy gap of the Unruh DeWitt detector, or rather, when you set the Rindler frequency, okay, to that energy gap of the Unruh DeWitt detector and the temperature of the Rindler bath to the Fulling-Davies-Unruh temperature, these things collapse identically to each other, right? So by covariance, we have that these two things are the same process, okay? And you end up with this identity that the statement of detailed balance in the lab frame unwinds to this thermal statement here at an arbitrary temperature of the Rindler bath. And so we have that Boltzmann factor in the previous slide, unwind that back into this expression, set this parameter as a best fit parameter for our theory, and we can measure the temperature of the Rindler bath from the data set, okay? This was a proposal by, sorry for doing that, this is a proposal by Gabby Kozel and all these guys about how to directly measure the Unruh temperature, confirm that you're interacting with the quantum vacuum, and you even know the process that's occurring, the emission and absorption of these particles set by the frequency and amplitude of that co-moving oscillation, okay? So now let's look at how we actually analyze or apply the theory to the data, okay? So there's our power spectrum. We have that detailed balance, which is gone. We have our thermal factor here, okay? First things first, since we're dealing with radiation reaction, right? We have this photon kick that's coming from this, okay? Using relativistic Newton law, you have the recoil acceleration, omega squared over pi m, okay? So that's the acceleration scale we should expect to be finding, okay? Now for our best fits, we want an overall scale factor to take into account detector efficiencies, detector lifetimes, things like this. That overall acceleration, number one. Number two, the temperature. And we should expect these two things to be related by the Fulling-Davies-Unruh temperature, but we measure it directly from the bath. Now our energy gap, right? We have a couple grips into what this thing should be. First of all, we know this idea about some sort of recoil kinetic energy, right? But we want to do something a little bit more involved, right? We know that from the example of anomalous Doppler effect, that co-moving oscillation should present itself as a constant in that energy gap. We have that fiducial Rindler term here, okay? I believe I have it written out here. And then the omega squared term, this thing should look something like recoil, right? Up to the hypothesis, right? And so this is the energy gap that we use, which is essentially just a Taylor expansion of whatever process is going to be occurring, right? There's conservation of energy, there's dispersion relations, it's all there. We don't know what it is, but we take a guess at it, okay? We include an additional cubic term. This is something that we don't know, some cross terms, some higher order terms, don't know what it is, but we included it just for the sake of completeness. So with these parameters, we perform best fits, okay, and then compute the chi-squared of those best fits, okay? First thing we have to do those, we take the best fit of the entire spectrum, and from that, we use it to compute the thermalization time. Just like when you put a thermometer in your mouth, you have to make sure you have enough time for the system to thermalize, okay? This has been the one thing that's basically wiped out any of the previous attempts at measuring the Unruh effect, right? You have to have acceleration lasting long enough for the system to thermalize. Whenever we look at that thermalization, the lifetime is a function of frequency. This is how much time it takes for each frequency to thermalize, okay? Of these co-moving oscillations, okay? The blue line here, or the light blue line here, the dotted line, that's the thickness of the crystal, 3.8 millimeter thick crystal divided by the speed of light, okay? Very short time scales. But we see that there's a hard cutoff at approximately 22 GeV. Below this cutoff, the system doesn't have time to thermalize. Our theory cannot apply to this, okay? We have a thermalized theory, it doesn't apply to this. Below it, perhaps the theory will apply quite, perhaps, well, at least we have an option to apply to it, right? So that means that we have to take low energy cutoffs of our theory. So we do at multiples of 10 GeV and compute the chi-squared as a function of these cutoffs, okay? And you see a rapid convergence of that chi-squared to below this one standard deviation threshold. This is reduced chi-squared per degree of freedom. That's the theoretical value minus the expected value divided by the error, right? And squared, right? And so whenever you see this thing converge to 1, that means that on average, the theoretical curve lies inside the error bar of all the data points, okay? Red here, these red ones, is whenever we set the energy gap to 0. So this is like a Bremsstrahlung theory. The black is the standard one that I showed before. The blue ones is whenever we best fit for the Rindler temperature as well. And we see that the fact that these things are already on top of each other shows that this Rindler temperature looks like it's going to be the Fulling-Davies-Unruh temperature, right? So we have this convergence to 1. Yeah, historically speaking, this thermalization time has been one tough thing to crack, to beat, to see the Unruh effect, right? Above 22 GeV, we're okay. Below we're not, and we see this rapid convergence above that 22 GeV threshold. So now let's look at the first. Oh, and I think there's a transient regime here. I did best fits for all for cutoffs at 20, 21, 22, 23, and it's very stiff. It was hard for it to go below, but at 30 was the first one. Okay, so let's look at the 30 GeV cutoff.
Sorry, before we go further, may I ask about your questions? So
Yes, ma'am.
the reason you chose the 10 GeV steps was because of what you just said, that it was
so there has to be a low energy cutoff, and so what do we do at 2, at 4, at whatever, and because these things take it was like 2 to 3 hours each of these best fits to run. So to save time, it was just an integer multiples of 10. Yeah, but then I went back and I even looked at that region in here and ran each of those, and it still stayed very stiff. It didn't go through, so I just left it like that.
I see. So the fact that at the low frequency your method shouldn't be applied or can't work, does it have anything to do with a few slides back, I think it was your slide 17, when you were showing or fitting your data with here? Does it have
the low energy. Okay, so now I'll give the cards away right here. This is the one that most because the Unruh effect, whether or not it's a classical or in the Rindler frame, it appears to be a quantum effect, but in the lab frame, it looks like it's a purely classical effect. I believe it comes just strictly out of special relativity, out of Lorentz invariance.
Yeah.
Okay, so it should be present if you have if the Unruh effect is there in the data. If it's there, then if you have a theory which encodes it somehow or in some regime, it should be accurate. And that's why I think this one fits the same way. It's there, they just don't realize it. Or they just didn't know that it was there. And the thing is, they had the ad hoc subtraction of the frequency of the photon from synchrotron radiation that they subtract by hand. We have the ad hoc omega squared over 2m in the energy gap, just by hook or by crook, just trying to get a handle on the thing. And these are, I think, conceptually very similar processes. And we have a transverse oscillation, they have a cyclotron oscillation, but that's like Landau levels or harmonic oscillators. It's the same thing, you know what I mean? And so that's why I think that these things are comparable, and that's why I think this one's the best.
I see. Okay. And while I have you on questions, could you go to, I think, your next slide? Yeah, here. I'm still a little bit lost why the temperature and the frequency are completely independent from each other. Because I thought.
Okay. Yeah. Go ahead.
Just the frequency and the amplitude of the oscillation gives you the energy, right? Yeah.
So you have a thermal bath with, in principle, an infinite number of energies there, but a thermal distribution, right? And whenever you have this, you only couple to those ones that you're talking to, that with your same frequency. Yeah, you resonantly couple. It's by delta. And when you do the math, it's a delta function.
Yeah.
Conservation of energy. Yeah.
I see. Okay. So then, this is the one. Once I've chosen my frequency, then I already have sort of fixed the temperature as well, or the temperature that I'll be reading.
The temperature is, in a sense, okay, so the temperature is going to be just what the Unruh temperature, so there's no communication between those. But in our situation, the temperature is from the recoil acceleration, which is dependent on the frequency. So in general, no, but for us, sure, yes, yeah. In some regime too, like I'll talk a little bit about how that, I don't know if it's each one or if there's a general, like an average temperature or something like this, but this is more of the details to be fleshed out, I think, of trying to understand these systems in more detail. Yeah.
Thank you.
Yeah. This was in trying to understand these things. I mean, because it's a very complicated system. It was just more of whatever grip I could get on the thing, just hang on for dear life, and then just slowly, pick away at the problem. You know what I mean?
Can you comment on how much data there is available for doing these chi-square fits?
So there's 149 data points, and then except one of them is the 0 data point, so 148. So number of degrees of freedom is 148, 6-parameter best fit, 7-parameter with the Rindler temperature one. So 6 parameter best fit. 140, whatever, yeah.
That's a lot of parameters for a relatively small amount of data in that sense. Well, why is there such little data? Why is there only 148 data points?
Okay, so I say data point. I mean, if we're talking about, okay, how do I say this? Number of, like things in the bin. I don't know how much data goes into each bin.
Okay, sorry. You have 148 bins. All right, that's okay. All right, yeah. 148 bins is much better. Yes.
Yeah. And
the errors on each bin. The errors on each bin are how large?
The errors on the bin are we have each bin width is essentially 1 GeV.
Yeah, but how? I'm trying to say how precise can you be with regard to the error? You're fitting within the errors, but it depends for me to. I need to understand how large the errors are.
Okay, I guess the bin error is going to be. I don't know what the bin error is going to be, but the error bar, the vertical error bar is.
Vertical error bar is what I'm looking for.
Yeah, it's like I think it's 0.1, 0.1, and some of them are 0.01. They're small. They're smaller than the dots. They're smaller than the data points. Yeah, they're very small. Yeah.
Okay,
yeah.
All right, that's what I'm looking for. Okay, thanks.
And I got the data from the first author, from the group. I got the data from the group. Yeah.
Very good.
Also,
okay, thanks.
You had mentioned whether or not we don't have much data. We have a 6-parameter best fit. One of the things that we were concerned with is whether or not we are overfitting the data, right? And what we'll see later on at the end, there's more mysteries, and in fact, the chi-squared gets worse as we have higher energy cutoff. So less data, worse chi-squared. So I'll show you that.
Okay, no, that's good. Actually, 148 isn't so bad. You're trying to fit 148 points with a 6-parameter curve. That's not so bad. Yeah.
Okay, yeah. I should also say too, we had chi-squareds of 1 on. They presented Bremsstrahlung as well, and so 1-parameter best fit for the overall scale, which usually which always came out to be 1 because it's normalized. But so even with the 0-parameter best fit, we got the Bremsstrahlung good as well on this analysis. Okay, so here's our chi-squareds. The chi-squared's the only one that's even remotely you could talk about, but this is the same one that's the quantum radiation reaction model. So I think, they have, this is a 3.8 millimeter sample. There's a 10 millimeter sample, which for us wasn't thermalized, so we couldn't do it. But this one actually gets brought down to, I think, 14. This actually ends up being the best one for their analyses. Okay, but yeah. Okay, and then low energy portion not thermalized, high energy portion thermalized. And so this begs the question: are we able to see some sort of onset of thermality? Are we able to see something like the information burning away, where this stuff is channeling radiation, this stuff is Unruh radiation? And if you kind of squint your eyes, you can see it a little better here. You see that comes up, there's a bump, and there's this other little hump right here, which might be that onset of that thermality. And so there's all sorts of questions which you can ask this then. Is this a window into information loss? What sort of things can we do with the fact that we have a data set where some of it's thermal, some of it's not? Is there some other information that we can get from this thing? Okay, so now the parameter analysis, right? We have a couple pieces of information. Let's go ahead and look at this thing really fast. I'll talk about this in a second. Okay, so look at our best fit parameters. Okay, first things first. Measured overall scale is 12.3. I look at my peak here, all the way up, look across 12.9. Okay, so that's the overall scale. Next thing, recoil acceleration, the kick, okay? Just take some characteristic frequency, photon frequency, at 100 GeV. 100 GeV squared over pi m is 6.2 PeV. Incredibly large accelerations, okay? Very large. But when we find our best fit accelerations for the 30 GeV cutoff, these are the parameters for 30 GeV cutoff, okay? We get 7.9 or 8 PeV. So this is something that it's on the same order of magnitude, but it's something so gigantic that the fact that, that we're getting things similar is I don't want to say a strong indication, but it's consistent with what we would expect.
So, and if you take 140 or 60 instead of 100, do you get something similar?
Yeah. No, you can. I just didn't want to look like I'm fudging it to look like the best fit one. But yeah, no, I mean, if we take I forget which one, I'm pretty sure I did compute that, but if something like maybe 70 or something like this, it'll give you this number.
So you're getting something that's roughly constant acceleration.
Oh, excuse me. No, it's going to be, so the question is it frequency dependent? And in principle, each photon should be thermalized at its own acceleration produced by that recoil, right?
Okay. Oh, I see. Yes.
Yeah, but so now the thing is I mean, that's another layer of complication in terms of, so we just did each one just has an average acceleration. Yeah, so
okay.
No, this is as you refine and make it absolutely. Yeah.
Okay, I see.
Okay, so then now, next thing is the co-moving oscillation, right? So you have a transverse harmonic oscillator. So in the co-moving frame, we should expect something on the order, say, of maybe 10 electron volts as a maximum, okay, as you have this tower of harmonic oscillator states. What we get is, the measured is, this is in units of GeV, but when you unboost it, this is about 5 electron volts, okay? So we should expect something less than 0.004 in these units. The fact that we get this is consistent with what we would expect, simply consistent, okay? In principle, you should, if you have the initial beam angle and things like this, that's a parameter that you can compute, which we didn't do though. I don't even know how to do. But here's the kicker though. That's the co-moving oscillation. That co-moving oscillation multiplied by the amplitude of that oscillation gives us that fiducial Rindler term that we're emitting and absorbing from, okay? So I take this number, I multiply it by the lattice constant of silicon, 5.4 angstroms, and I get 0.11, and this is our best fit parameter for that constant as well. So we have something in very good agreement with that, okay? So that means that we're in reasonable agreement with what we expect for the constant term, and then that fiducial Rindler term. And then last but not least, for the A square, the recoil term, 1/2m in inverse GeV is 978.2, and we get 846. So not the best, but still within reason, okay? But that's up to all of the, I guess if you want to call it maybe confusion of whether or not it should be omega squared over 2m for recoil, if there's other processes that's happening. And so our guess for this energy gap as being a constant co-moving oscillation, the fiducial Rindler term, and then something that looks like recoil is at least within agreement from what we find from our best fits, right? The higher order term we're not terribly sure about, but at least I just presented for completeness. But this is going to be some cross terms, some higher order term. Okay, and so then now finally, let's just look at the temperatures, okay? So if I average the accelerations, I guess if you want to average the average accelerations for each cutoff, so from 30 at multiples of 10, 30, 40, 50, 60, all the way up to 100, okay? I get an average acceleration of 1.8 PeV, and the error here comes from the standard deviation of the mean, okay? And then if I do the average of the best fit Rindler temperatures, where we specifically leave that temperature arbitrary, we get 1.96. And so again, standard deviation of the mean for the error. And so then when we just find that the temperature of that Rindler bath is the Fulling-Davies-Unruh temperature plus or minus about 0.4, okay, in terms of that standard deviation. The upper bound on the temperature is 2.23 PeV. That comes from the highest frequency photon. That's the first photon to thermalize. I also want to point out, just because you can see it a little more clearly here. Oh, and one thing I should say, this temperature, this FDU temperature, the Rindler temperature, this blue dotted line here, okay, is that best fit Rindler temperature that we get from the best fit, okay? If we deviate that by even the slightest, by 0.10, by like say 10% here, right? That's these two pink and purple curves here. It's very, very, very sensitive to the temperature of the Rindler bath, okay? So the fact that we get this thing is very good, strong indicator. Okay, and I think that it's nice to say that at least this proposal put forth by the Brazilian guys for measuring this, at least, you know, at a first stab of it, works quite well. And so this might be a very good indicator that we actually saw this the Unruh effect in this Fulling-Davies-Unruh temperature. Okay, so now there was a question earlier about Bekenstein-Hawking area entropy laws. If we have the Unruh effect there, okay, that means there's a Rindler horizon. And we're emitting and absorbing radiation into this Rindler horizon. And all of the stuff that passes through this should change the area of this Rindler horizon. So we should see some sort of horizon dynamics from this thing, okay? There's a little bit to say about how we're doing this analysis that I'll talk about in a second, but in general, each photon, okay, or the temperature will go like energy to some power. Here we have an omega squared because of the omega squared temperature, right? And so if we just plug this into the second law here and just integrate it, we get something like E final minus E initial to some power, okay? And then the change in area, okay, which is the energy momentum which gets fluxed through the horizon, okay, given and then sourced by these null vectors who get geodesically deviated by the Raychow-Urey equation to bend out to create the area change. Okay, this is the area law, the change in area that we get. So the area entropy ratio is given by this delta energy, which is the energy that gets put into the horizon, and then the E final minus E initial is the difference in energies between those two states. So what we do now is we want to take our power spectrum, integrate it, okay, with an initial and final energy, and integrate that area, and then plug it into these equations and see if we can see a convergence to 4. I mean, we have the Planck area here, but it's set it equal to 1. So let's look at the one that we have. So we have the squared term here, okay? This is the area entropy ratio we have. This one is a little bit more clear about how that the change in area works. You have the geodesic deviation, and then you trace the rays back, and that's how the area changes occurs, okay? And so by integrating the data, we see, again, something that looks like it converges to a 4 at that 22 GeV threshold, okay? Now, this is, I guess you'd call it an initial attempt, very, very, I don't want to call it ad hoc, but I think there's a lot more physics here to be worked out. This thing, it's a very flat thing, so it's very, very sensitive to, if I switch things by some constant, it'll move this thing around or deform this spectrum a lot, okay? And this is actually a source for, I guess you could say, a lot of issues for what we're working on right now, and I can show you what's happening with these things in these later slides. But what we do have, at least initially, is it looks like a convergence to 4 above that same 22 GeV threshold. To get this 22 GeV threshold, by the way, you have one of the things that convinced me that we were on the right track with this. When you look at something like, say, back in grad lab, when you look at muon decay, right? You have to take into account the speed of light in cables, 1 nanosecond per foot, in order to do the correct timing in these particle physics detectors, right? This one, in order to get this, I had to take into account the thermalization time for the 150 GeV photon, the highest frequency photon to thermalize. That's the one that you have to, the time that you're in the crystal up until that moment is not thermal. So you have to subtract that off, and that's when it snaps it to this 22 GeV. So that's why I was like, okay, so at least there's something that's consistent with what we would expect for these to work. So, okay, so then let's talk about what we can do in the future, okay? There's more, so future outlooks for what we can do, okay? I got a couple of extra slides, but what we have now, at least tentatively from the paper that we put out, is that you have these Parker-Hawking and now Unruh effects that are being studied experimentally, okay? And so what the future has, though, I think is going to be a lot more interesting, at least from what we're working on now, okay? There's more data sets, okay? At different beam energies, 40 up to 80 GeV, okay? Different crystal thicknesses, and so there's all sorts of samples to analyze. But most importantly, these are already been published, okay? These have different incident beam angles, okay? So when you have your lattice site, if you change the angle, it modulates the amplitude and frequency of that oscillation. So that incident angle that comes in gives you a way to modulate the energy gap and tune that interaction with the Rindler band. Okay, so this is a very, very strong kind of knob you can have on your experiment here. And so one of these things is that I would like to do is to analyze these data sets as well. Now, okay, so let's talk a little bit more. So there's a lot of stuff about overfitting, degrees of freedom with data points, this area entropy law. And this is all boiled down to what I'm just calling the high frequency tail anomaly, okay? If you squint your eyes a little bit, you can see there's a lot of these black data points which are sticking up above the tail end of the curve, okay? And if you see it in the spectrum, actually, from their data set, so if I take their power spectrum and divide it by frequency, I get this set here. And if you kind of squint your eyes right here, everything above kind of the diagonal line of my cursor, that's an excess, that's a bump in the data. There's something there, okay? And that's reflected in our chi-squared. Okay, this is one of the things that convinced us that we weren't overfitting the data, is the chi-squared should basically become perfect the less data points you have. And in fact, it becomes worse the less data points you have. And that's also reflected in that area entropy law. We see this gigantic divergence in this high frequency tail. High frequency tail excess, high frequency tail, and all four of these things that we're looking at here, right? So then the question is what could be the cause of this? And this is what I'm working on now with Uwe, is there some non-trivial dispersion relation that's occurring? When you have your atomic sites, you have the atomic sites, you have the electric field from these atomic sites. Since you're relativistically boosted, these atomic sites get smeared, okay? And on top of that, your electric field then gets enhanced by a factor of gamma in the transverse direction that the positron moves through, okay? And so you can get some vacuum polarization due to the strong electric field that's being sensed by these positrons, okay? And, oh, thanks, okay. And so if we take the Euler-Heisenberg dispersion, this Euler-Heisenberg length you can get from, this was, I forget actually who got this. I know it was Mati Sega, was one of my old advisors at Technion, but that the Euler-Heisenberg length is just gauged by the electric field with this factor of gamma. These kappas, it can take on two values, 14 and 8 for the different polarizations. And oops, sorry. And here you have your critical electric field here, but we were able to unwind this to get the index of refraction from these systems. And what's important to notice is this arc sign here. Since this thing has to be less than 1, this gives us a cutoff in the spectrum, okay? A hard cutoff, okay? And what we can see then is if we assume that this cutoff here, okay, is at 150 GeV, which is the last data point, right? Now recall that we have 178.2 GeV. So that's 30 GeV of desert that we don't have any photons from. Why is that, right? Is that potentially due to this cutoff that comes from this Euler-Heisenberg length? That would be at a Euler-Heisenberg energy of 386 GeV, but the cutoff is at 150, right? Here's our dispersion relation, and here's our index of refraction here. But if we incorporate that, at least now in the area entropy law, we see that it tempers down that high frequency tail, okay? We still have this excess here, and kind of a full disclosure, I suspect that this excess is due to either numerics or an incorrect implementation of that area entropy, the way I'm integrating it, that there's something wrong with the way I'm doing it. But the fact that we even get this here means that we're at least on the right track, right? So not trying to make full claims of anything yet, but there's a strong indicator that this Euler-Heisenberg might be there, that it's the cause of that cutoff at 150 GeV. And so this is what we're doing now. This was basically the beginning of the week. This is where we were at. And so I kind of switched gears to prepare for this presentation, but we're going to go back now and we're going to incorporate this Euler-Heisenberg dispersion in the power spectrum and compute chi-squareds and do the same process there as well. See if we can get a grip on this thing. But I'm hopeful because of this cutoff, actually, that this is why the 150 is the cutoff in the data set. Okay, and so that's kind of the story of what we have up until this point. So just to kind of give conclusions, we saw that we have a nice grip, at least on the recoil acceleration. We have these gigantic PeV scale recoils, and we get best fit measurements where at least on par. Is likewise with this recoil, we have something that's at least in quasi agreement for this presence of recoil. We're able to measure that Fulling-Davies-Unruh temperature directly from the bath and confirm that it's the Rindler temperature is the Fulling-Davies-Unruh temperature with that chi-squared to match it. The area entropy law, although it seems a little bit pathological at the moment, does look like it's converging to 4 and is obeying at least the way we think it should obey. And so this is where we get the, I guess, the evidence for, I will say, a tentative claim or a tentative indication that we see that the Unruh effect is there in this channeling radiation. There's more data sets from NA63, and it's even on their website that the concepts that are studied at NA63 even apply in a gravitational analog, Hawking radiation from black holes, which remains to be detected. So this is something that they were expecting to see, and it looks like that they were actually successful in this 3.8 millimeter sample. So I guess thank you guys very much for your time. I'll give a little bit of one more kind of stay tuned thing. I was able to work with Denjo, and I'm very appreciative of that, to put out a Royal Society fellowship application to work with lots of friends and collaborators here. This was backed also by Ulrich Ugerhoch, who is the PI of the NA63 collaboration, with support from George Matzes, who is the guy who proposed the experiment, the type of experiment to measure that Unruh effect. And then working with Nayesh Afshori and Ellie Cohen, who was a co-author on the paper and a mentor for me when I was at my postdoc. So we have a fellowship application out to continue this pursuit. And so so thank you for the advocacy and thank you for your time. If there's any questions, I'd be more than happy to answer.
Great, thank you very much, Morgan. And the floor is open to questions. We like to ask the questions as we go, so.
Okay, yeah, it's all good.
And I'll put in the name in the chat.
Oh yeah, I saw that. Yeah, I wanted to get that.
Bronstein, he says, is the person.
That's actually it's funny. It's it's sad, I guess, but I think the other one was it Schwarzschild, who I think he died in the trenches in World War I from some flesh-eating disease after he had worked out the solution for the Schwarzschild solution for black holes. These are interesting stories from history.
Yeah, well, yes.
Yeah, that's what I always say. Theoretical physicists have to try to stay healthy.
Yes, yes.
That was a very good talk. Thank you so much.
Yeah.
Yeah, I asked a lot of questions, so I'm leaving room for it.
I appreciate the opportunity, and one of the things I don't want to overstate anything. It's a preliminary analysis, and I believe kind of in my heart of hearts that this thing is there, but there's a lot of physics involved in these things to unravel, and I think we have a nice little grip on it right now, but there's a lot more to do, and I'm very excited for the opportunity to work on these things, and I think this Euler-Heisenberg stuff we're working on now is very promising, and so it's yeah, it's fun. I'm very happy to share all of this stuff with you. I definitely appreciate the opportunity.
Oh, absolutely. I mean, your excitement comes through, and yeah, it's very captivating.
It's bad. I had to open a window. I'm getting all sweaty from it,
I don't want to dominate things, but are there questions from anyone else present at the moment? Just to. If not, I'm curious to know, what is the longer term plan for this experiment?
So the experiment, I believe, I don't know exactly what they're doing, but I believe it's just ongoing. They're going to keep on analyzing different samples, different beam energies, higher energy beams and stuff like this. I think, I mean,
presumably going to higher energy beams is even better for you.
Yes, I believe higher energy beams, the higher energy of the beam, and I think also a short crystal. There was actually a curious thing. There's a 3.8 millimeter thick crystal. There's a 10 millimeter thick crystal. The 10 millimeter thick crystal, the thermalization time we weren't able to uphold it there. And so that was actually, I guess what happened.
But with a higher beam energy, you should be able to.
Yeah, I'm hoping so. Yeah, and that's the other thing I'm a little worried about is these guys over here are at, where is it? Hold on. Is it here? Yeah, these ones at lower beam energy, the 50 GeV, maybe the 80 GeV one will be okay, but if it's some average energy that gives you, or average acceleration, because we had the 100 GeV that we used as kind of our characteristic acceleration. But if it's an average like that, you need the higher end of the spectrum to get the strong enough acceleration to thermalize. And so I'm hoping that these guys will be strong enough as well. And so that's, again, yeah, the higher energy, the better. But lower energy, like, okay, maybe the 80 GeV will be okay. But this modulating this incident angle, I think, will be very, very strong indicator, because that's literally tuning the interaction with the Rindler path. That's the one that I think is going to be very interesting in the future. And yeah, I mean, I know they do other stuff. They have they use bench crystals, so they have the crystal, but I don't know exactly how they do it. I think they put strain on it, and so it acts almost like a curving waveguide for the photons, and so you get really strong radiation from a rotational acceleration as well. So I know they do experiments like that. So there's a wide array of these things, but what specifically their goals for the experimental group are, I'm not too sure of. But yeah, the bigger the beam energy, the better,
So I have a question about the circular Unruh effect. You started mentioning that.
Yeah.
So are you familiar with, let's see, 2020 paper Biermann?
Is this the one with Unruh down at A&M and Jorma and these guys?
Biermann, Ernie, Gooding, Luco, Unruh is one of them.
Yeah.
Circular Unruh.
I'm moderately familiar. Yeah, that they're making the analog DEC measurement of the effect. Yeah, I'm actually very hopeful that they can pull this one off. But yeah, I don't know exactly how close they are with these things. But yeah, I'm probably reasonably sure they're going to be successful in that. Yeah.
Yeah, I hope so. So the work I'm doing, I'm actually using the circular Unruh effect to do nuclear modeling. I've come up with a new approach in nuclear modeling, which kind of like, we're trying to claim it explains the origin of quantum chromodynamics. It's like, so you know how if you have pair production, right? You got the photon interacts with the nucleus, and then somehow it mysteriously generates mass and charge, color charge, right? Comes out of nowhere. So we're trying to model the generation of mass, charge, color charge, etc. And we're using the circular Unruh effect to generate the mass.
There's I can refer. Are you familiar with the work from Karzaev?
No.
So and he has a co-author. Karzaev had looked at and because when you look at heavy ion collisions, okay, so I believe it's high PT, low rapidity jets out of hadronic collisions. Okay, so you crack a nucleus and you spit out just a jet of pions and stuff like this, right? You have this the QCD string, basically the QCD confining potential, which produces gigantic decelerations. Okay, and they applied it's kind of a quasi string breaking model, but with Hawking interpretation to it. And it does describe their data actually quite well. The fact that you can, like as an example, you can never pull, say, quarks out of a nucleus sounds almost like a black hole, that you can have like a colored black hole, And so there might be some very interesting physics that you can flesh out with that. That I had long thought that somehow in some limit, like strong field QCD, excuse me, would be something like an Unruh effect theory, because you have such strong confinement that it's now a classical acceleration. And so you start to see things like this. Like, yeah, I wouldn't be surprised if there's a lot of real physics to flesh out in those systems.
Yeah, I've got a paper currently going through peer review. I've had real good response with it. I'll send it to you.
Yeah,
I
sure,
just finished version 2. I'll send it to you.
Okay, cool. Yeah, awesome. Yeah, I should also comment, that was one of the reasons. So my background originally was in nuclear physics. I was looking at dilepton electron-positron analysis from quark-gluon plasmas. And I guess that you can use ADS-CFT to apply to QGPs. So if you have, an ADS space, if you have a black hole with Hawking radiation, that'll set the temperature of the conformal field theory on the boundary. And quark-gluon plasmas are at high temperature QCD are approximately conformally invariant. And so you have applications of Hawking radiation to those systems. And that was how I got into Unruh effect originally, was that analog Hawking radiation type of thing for quark-gluon plasmas. Well, if that's there, maybe Unruh effect is there as well.
Yeah,
So
exactly. I'm actually trying, currently my new work is trying to describe the quark-gluon plasma of a deuteron. Are you familiar with the Phoenix collaboration?
Yeah, I did.
Right.
Or what?
Yeah, the Phoenix collaborations data.
Yeah, I did dilepton working group. I was on the beamline. Yeah, I did all that.
Oh, okay. So
yeah.
The deuteron, they got this curious hourglass shape.
Oh, yeah.
Yeah, so I'm trying to model that using a new approach that involves Unruh, circular Unruh effect, and some other thing, like throwing together a bunch. I'm actually using quantum electrodynamics, quantum field theory, tying it into quantum chromodynamics. I mean, I'm trying to connect a few things, but
yeah, no, it sounds like a cool idea, actually.
Yeah. Anyway, nice to meet you.
Yeah, definitely. Nice to meet you too.
Excellent. Thanks, Morgan. I'm going to stop the recording.
Okay.
because we've probably plenty at this point. Okay,
Yeah.
thanks again for giving the lecture. Much appreciated.
Yeah, appreciate the opportunity.
Okay.